All right, welcome to the first video of 9.3. We are going to talk a little bit more about the graphs of logarithms. Now, we actually started our logs conversation with a graph. If you recall, what is a log at the end of the day? It's something that undoes an exponential function. Okay, so we have something like log 232 equals 5 because 2 to the 5th is equal to 32. This is something that we can see the inverse of an exponential, all right? But that doesn't mean we can't take a graph of it. We can take all the logs of 2, right? If we did something like log 2 of x, well, we could get a whole bunch of answers, all the things. We could have equal to y, and we could graph that. You can do this with any base, and so we get this sort of generic formula, log base a of x is equal to y. And then, as usual, we usually put y first when we're trying to graph something, so you can see we just flipped it around here. Whoops. Let's see what these bad boys look like. Stop it. Example 1, graph the following logarithmic function, log base 3 of x is equal to y, by creating a table of values. All right, so first off, same thing as y is equal to log 3 of x. Let's go ahead and just create a table of values. We don't know any fancy tricks like slope or y equals mx plus b for these, right? We don't even know what these parent functions look like yet. So let's just go ahead and create a table, x and y. We'll choose some good ones. We usually go with kind of centering around the middle of the x's there. All right, so log 3 of -2 is equal to y. So now I've got to solve this, right? So let's transform it back. So what power of 3 becomes -2? Oh, that's a hard one to solve. You know what? I don't think that's the easiest way to do this problem. I think this may be a little bit different of a situation, right? What would be a nice, easy value to do there? I don't really know. I think it might be really hard to come up with the x's for this function. So let's not do that. Let's do a fresh one. I left myself no room. Over here, it looks like, according to this right here, it looks like it might be easier to choose the y's than it is to choose the x's. So let's choose the y's. Let's choose those same numbers, but let's put them on the other side and see what happens. If I do that, what do I get? Well, I get 3 to the -2nd is equal to, oh, I've seen something like this before with exponentials. 1 over 3 to the 2nd, which is 1/9. We could see 3 to the -1 is 1 over 3, by definition of a negative power. What's 3 to the 0? Anything to the 0 is 1. 3 to the 1st is 3, and 3 to the 2nd is 9. So in this case, we chose the y's, and we got the x's. We solved for the x's. There is no rule against that. It's just usually x is our independent variable. X is the thing we usually plug in and solve for. But there's no reason that has to be the case here. If it's easier to find the y's before you find the x's, then go for it. I'm still going to plot these as x comma y though. Still going to plot this as the x-axis and the y-axis, okay? So let's go over to the x-axis, or to the graph now, and actually draw an x-axis. Better than that. And down the middle. Boop. All right, what's unique about this is I'm looking at my table now. I'm not seeing any negative x values. Fascinating. But let's plot what we do have. We have out just itty bitty little bit and down 2. Out 1/3, down 1. Out 1 and up nothing. Out 3 and up 1. Out 9, 6, 9, cool, and up 2. And we see this beautiful log function. Now, why do I know this keeps going down? Why do I know it doesn't hit negatives? Well, if you remember, what we're plugging in are exponents. Since that base is a +3, I can't get a negative number out of an exponent. There's no power that's going to change a +3 to a negative number. Fractions, yes. Bigger numbers, yes, but I'm not going to suddenly change to negative numbers. And so what we get here is called an asymptote. We get a function that is just going to get smaller and smaller and smaller and smaller and kind of get really close to the y-axis, but not go over it. The same thing happens with exponentials, but we call those asymptotes. In this case, oops, pardon me, x equals 0. Now, why are you saying x equals 0, Ms. K? That's the y-axis. Remember, this is where x equals 0. It's getting closer and closer to x being 0, right? 1/9 is a very small number. It's getting closer to that, but it's never actually going to touch x equals 0. Cool. Let's do another one. So graph the logarithmic function log base 1/2 of x is equal to y by creating a table of values. Well, I already saw that choosing x's is going to be really hard. So I'm still going to choose the y's this time. Just for every log function, I think that might be a good idea. We'll just choose those same ones. All right, so let's look at our function here. Log 1/2 of x is equal to y, which means 1/2 to the y power is equal to x. All right, let's start with some the positive numbers. We're a little more used to that. So 1/2 to the first. Oh, that's easy. That's 1/2. 1/2 to the second. What happens when you square a fraction? You basically just square both parts. 1/4. Lovely. What happens when you take anything to the 0 power, even a fraction? It just centers off at 1. Lovely. All right, whoops. What happens when you take 1/2 and you flip it over? You get 2/1 or a whole 2. What happens when you take 1/2, flip it over, and square it? You get 4/1 or a 4. And we have our data. Okay, we have our points that we're going to graph. Let's go ahead and do that now. Draw some axes. Lovely. And I'm just going to plot what I have. Now remember, I'm going to plot it as x comma y. I'm not going to plot the point 2 1/4 just because I used 2 to find 1/4. I'm going to plot out 1/4 and up 2. Out 1/2 and up 1. 1 0. Out 2 down 1 and out 4 down 2. And we see that, oops, try that again. There we go. And this actually would probably hit 8 as well. There we go. Cool. Now, if you, just real quick, the opposite of this function, log base 2, would actually be the flip of these points. So if you want, for those of you who are really good at transformations, you can kind of think about this as like an upside down 2, a reflection over the y-axis. If that's not something you want to look at it, then you can just go with the table until you feel more comfortable with that. But when I'm doing these tables and I see 1/2 to the second power, I think, okay, wait, what's 2 to the second power? Let me turn it upside down. So it's up to you how you want to think about that. But what would be the asymptote here? The asymptote, it looks like it's the same thing. No matter whether it's upside down or not, we're still getting really, really close to x equals 1. Asymptote is still x equals, I'm sorry, we're getting close and close to 0. Closer and closer to 0. So the asymptote is still x equals 0. All right, let's do one more. We're going to state the domain. We'll do 2 more, pardon me. And then we'll move on to transformations. So graph the logarithmic function f of x equals log 5 of x by creating a table of values, and then state the domain and range. So this time we're using function notation. That doesn't mean anything changes. We're still going to use a table. We know that this is a function, which is great. We can plug in anything we want to y. We'll get numbers out. We can actually plug in anything we want to x, except a negative, but we'll talk about that. So -2, -1, 0, 1, and 2. All right, well, I've got this function, which means 5 to the x is equal to y, as seen before. So 5 to the 0 power would be 1. 5 to the first power would be 5. 5 squared is 25. And then I can take those 2 positive values, flip them upside down, 1/5 and 1/25. So you can see that these tables are not that bad to come up with, as long as you remember that that negative just flips the fraction. Just flips it right back over. All right. Oops. Go ahead. Having trouble drawing lines today. There we go. Boop. And totally missed that. That's great. All righty. So out Not even a fourth, like not even a little bit. We're just going to go a teeny tiny bit and get really close to the x-axis, or y-axis, pardon me. Down 2, 1/5, 1, out 5 and up 1, and then 225 goes way off the page. So we will go ahead and sneak closer, connect those dots as best we can. And again, we see that axis, that y-axis is acting as a border, and so the asymptote is x equals 0. Now, that's actually going to help us come up with our domain and range, which is the second part of this problem. The domain, we're seeing that the asymptote's getting really close to 0, and it's not jumping over that, right? There's no second half to this function. There's no way to get a negative out of that positive 5 base. And so this domain is going to be 0, the asymptote, up to positive infinity. We are only seeing the right half of this graph, right? But if we think about the range, the y values, we see both the bottom being hit, -2, -1, 0, and 1 and 2, because we can have anything as an exponent. And so we get -infinity to positive infinity as the range. All right. Now, for interval reminders, go ahead and reach out to your teacher or reach out to me, Miss Kennedy, and we can show you how to rewrite those. Let's do one more, another one, fractional base, but same idea. This time, going to choose those y's, same as the other times, right? Since it's a fraction, again, I can kind of think about this as a flipped over 3 to the x, but if you don't want to, you don't have to do that. Do 1/3 to the x. Let's see. 1/3 to the first would be 1/3. And then if I flip that over, that would be 3. 1/3 squared would be 1/9, both of those squared. Flip that back over, you get 9. And anything to the 0 power is 1. So hopefully maybe you can see some coordination there, use it to create that table quickly, maybe even in your head, and don't need to create that table every time you try to graph one of these guys. But, if you feel like you're going to make a mistake, you could also write it down. Okay, so now we're here. Again, I'm going to graph x comma y, and I keep coming back to that because that's what I see people do all the time. They always want to flip these because that's how they solve for them. So out 2, down 1/9 is not correct. It's out 1/9 and up 2. So like right, oops, not even there, like there. And then out 1, up 1/3, 1, 0, 1, 3, 1, -1, and 9, let's see, 6, 9, -2. Okay, and just to illustrate that point once again, take a look at example 4, which is a base of 1/3, and the very first one we did today, a base of 3. They are a reflection of each other over the y-axis. So we get that kind of cool relationship between the two. But did the asymptote change? No, it did not. We have still x equals 0. Which means, again, our domain we see as nothing on the left-hand side, so not -infinity, as I was about to write, but 0 to infinity. Now, why am I not making a bracket is because the asymptote is not something we actually hit, right? We're getting really close. 1/9. The next one would be 1/27th. The next one would be 1/81st. It would be super tiny, but not actually 0. You can keep cutting a fraction down forever. You will just get a very small piece. Not actually 0, though. The range, however, we do have both sides, so we see -infinity to positive infinity. That's what we'll close out this video. Next, we're going to take these things and we're going to transform them all over the graph. See you there.